All right, thank you everyone for coming. Today our speaker is going to be Antony Speranza from UIUC. He's going to be telling us about Brown-York charges at null boundaries.
All right, yeah, thanks a lot for the invitation. Okay, yeah, so I'll be talking about mostly work that came out this fall with Ben Chandrasekhar and Aina Flanagan and Ibrahim Shehzad. As well as some idea, it's sort of a follow-up from this paper from last year that I wrote with Ben Chandrasekhar. Okay, so basically to begin with, some of the broad motivations for what I'm talking about is essentially the thing I'm interested here is sort of gravitational charges at null boundaries. So some examples where these types of things come up. So you have something like a black hole event horizon. There's various constructions where you're writing down charges associated with diffeos that act near an event horizon. And in various contexts, you might find something like a Virasoro algebra acting near an event horizon, and this is well-known type of construction from like Strominger or Carlip, or the soft hair proposal of Hawking, Hago, Perry, and Strominger, where this gives you some idea about the black hole entropy and kind of a CFT description. Another situation where these types of charges come up are just like asymptotically flat spacetimes. So the null infinity or asymptotically flat spacetimes is known to be a null surface, and you're interested in writing down charges associated with things like DMS transformations. This is something that's received a lot of recent attention in applications, for example, to celestial holography and understanding maybe holography in flat space. More generally, you will have null boundaries showing up. They sort of naturally show up as boundaries of causal domains in gravity. So if you're interested in something like an entanglement wedge and observables associated with that, it's naturally bounded by like a null surface. So something like causal boundaries. And so, yeah, so like I mentioned, the charges that we're interested are associated with diffeomorphisms that are acting at a null boundary in a gravitational theory. So normally diffeos are gauge, so they should have zero charges associated with them. But when you introduce a boundary, whether it's asymptotic, an asymptotic infinity, or something like an event horizon, the diffeos that act at that boundary have non-zero charges, and they characterize things like the local stress energy in a subregion, or if it's an asymptotic boundary, of the whole spacetime.
So there's a qualitative difference between looking at things at an actual boundary, like described, versus a black hole event horizon, which is not an actual boundary in spacetime. Are you going to explain like how you're going to define the charges in one case versus the other?
Yeah, so, well, the idea is I'm going to talk about kind of a construction that specifically is for a finite boundary. I'll talk a bit about some ways that it generalizes to asymptotic symmetries. But the kind of the philosophy is just say you came up with some way for defining a subregion in your spacetime, and then you're looking at diffeos that act near that boundary, and you're trying to characterize things like the local energy density inside that subregion or angular momentum. And so for a black hole event horizon, there is a way to define where that is. And so that's a surface in a black hole spacetime. And then you can basically define the quasi-local energy inside the black hole from this.
Maybe gauge it again in some sense.
Yeah, so it's gauge and vary. I mean, I'm essentially not going to work too hard on telling you exactly how to define the null surface, but I'm saying once you know where it's at, we can write down what the quasi-local charges are. Essentially, you're saying, I'm going to give you a prescription that works once you're in a background. And so once you have a background spacetime, I can tell you where various null surfaces are. And you can
So
construct these
is
charges.
it gauge invariant up to, you're not allowing me to do diffs that move the null surface?
Yeah, so specifically, I won't consider diffeos that are moving the null surface.
Is there any reason to not allow me to do that, or?
For the most part, it's kind of just technical. There's also, when you do this for things like, if you were working in like asymptotically ADS, there's actually kind of, you'll work with diffeos that kind of don't move the actual asymptotic boundary, but kind of at any finite location, they are moving these cutoff surfaces. So there's definitely an interest in understanding the diffeos that move normal to the surface. It's just not, I mean, there's various ways to understand that. It kind of like induces, you can think of it as inducing a conformal transformation on the surface in some cases. But yeah, for the most part, I'm going to restrict to diffeos that preserve a boundary. And so, yeah, we just don't have to worry about that question. Okay. Okay, so yeah, so the idea is we're coming up with some prescriptions to write down charges associated with boundaries. And there's kind of two approaches that on their face look a little bit different for how to construct these charges. One, you might do what I would call a canonical set of charges. For this, you would like write down a phase space associated with a Cauchy surface, act with diffeos on that phase space, and you would see there's some charges that you can write down that are Hamiltonians generating that symmetry on that phase space. The second approach is what I'm going to be focusing on in this talk, is what I would just call the Brown-York charges. And in this approach, you write down essentially the action for a subregion, and you write it as a functional of your boundary metric, and you define a boundary stress tensor by varying this classical action with respect to your boundary metric. And so these Brown-York charges are kind of popular in their connection to holography, because various ways of understanding the holographic dictionary, this classical action really is related to a generating functional of your CFT, and then you just vary that functional with respect to the metric if you want to get something like a stress tensor. So, okay, just to spell out what that is, so you have something like the classical action associated with a subregion, and it's a functional of, say, the boundary metric of that subregion. So just a picture to have in mind is this subregion. Say here's some timelike surface, and then we've got a metric hij on that subsurface, and then the action is the action for this subregion, and then the stress tensor is given by the usual formula, where you vary this action with respect to the metric. And then from this stress tensor, you can construct another currents associated with a given diffeo by contracting the diffeo, this associated with a diffeo generated by this vector C into the stress tensor, and then contracting with something like the volume form to get a current. And yeah, like I said, this approach is popular in holography because it directly relates to things like the boundary stress tensor of the CFT. Okay, so and in general, when you do this, just next one. So these Noether currents, as if the vector C generates a symmetry of the boundary metric, so it's a killing vector for this boundary metric, then this Noether current is conserved. That's the Noether's theorem. And this conservation law basically actually has basically two terms in it. It has one term that looks like Tij dicj, which is 0 when this is a killing vector, and then the other term is the divergence of the stress tensor. And so what I'll be talking about a bit is that this conservation equation kind of relies on two pieces, one of which is just the fact that the stress tensor needs to be covariantly conserved as basically an equation of motion. And then the conservation of another current also includes this, this killing condition where this thing is 0. Okay, and so the idea in this talk is, so this is the standard description for when you have like a timelike boundary. And the goal of this talk is just to explain how this construction works for null surfaces. And the reason there's kind of a set of subtleties that all stem from the main point that a null surface is just geometrically different than, you know, some sort of timelike surface, in the sense of the geometric structures that you put on it are different. So the main subtlety is that this intrinsic geometry is something that has been called recently as an intrinsic. It's called Carrollian, as opposed to pseudo-Riemannian. And so I'll discuss what exactly that means. And so because of this formula where, since your intrinsic geometry is not really just characterized by this metric here, you need to kind of generalize that formula. So it's Eij is not just the variation with respect to the metric. And so one other subtlety related to this, the fact that the geometry is Carrollian, is this equation right here takes a little more work to define what that means, because this equation here requires a notion of a covariant derivative. And so when you have a Riemannian geometry, you just have a unique covariant derivative associated with that. But when you have this more general structure associated with a null surface, well, it's not more general, it's just a different structure. It's not clear how you should define this covariant conservation equation. And the final thing, okay, this is related. So the induced metric is degenerate. So call that Qij. So it has null directions, and all this means is you have to be very careful with the index placements, because now you're not allowed to raise and lower indices with the metric as you might be used to. And so these are kind of subtleties that you have to address when doing this entire construction on a null surface. And so just to give you the answer, this question of a covariant conservation equation will show that there's sort of a connection independent way of defining this type of equation on a null surface. And then we'll also show there's a class of preferred connections that are induced on null surfaces when they're embedded in spacetime, in which case the equation reduces to something that does look just like this. For point number 2, there'll just be a more general formula to associate with the stress tensor, and kind of the principle behind that is the stress tensor. It's not necessarily just measuring how your action depends on a metric, but it's measuring the response of your action to diffeomorphism. So there'll be kind of a precise way of extracting a stress tensor, even when the geometry is not, is the one associated with the null surface. And then this thing about the index structure being important, the answer is the stress tensor naturally comes to you as a mixed index object, and it'll have a very nice form when you make sure to define it with the mixed index placement. Okay, so that's kind of the goals for what I want to explain. And so the idea is I'm gonna just go back through the Brown-York construction for the timelike surface and try to set it up in a way that can be generalized for the null surface. And then I'll try to explain what this Carrollian geometry means and why it shows up at null surfaces in gravity. And then hopefully I'll get to the construction of the Brown-York stress tensor on the null surface and the charges as well. And maybe I'll mention these two types of charges here. in principle, they're constructed in different ways, but one of the things you can show is that the two charges agree in, subject to a certain covariance condition, but that's sort of the final step, is to show that the canonical charges agree with the Brown-York charges. So in the end, you're getting the same thing. Okay. Okay, so let's just do the timelike case again in more detail. Okay, so let's draw the picture that we have in mind. So we're considering some subregion U bounded by a timelike surface T, and there's going to be a metric Hij on this boundary here. So the Brown-York construction starts essentially with the action for the subregion. So what you do is you write the action for the subregion. It's the integral of a bulk piece plus an integral of a boundary piece, which we'll call little l. And then I'll say plus, in principle, you also add terms at the future and the past boundary, and there's additional terms coming from the corner. And while those things are interesting, they're essentially not relevant for the actual construction of the stress tensor. So they're I'm going to sort of drop terms that localize at past and future boundaries, basically, for this talk. And so for GR, your Lagrangian is just the Einstein-Hilbert action. Okay, so it's Ricci, scalar, cosmological constant, and a volume form on spacetime. And then the boundary term here, we picked the boundary term that's associated with a Dirichlet variational principle. So that's going to be the Gibbons-Hawking boundary term. Okay, and then eta is what I'm going to call the volume form on the boundary. Okay. So, like I said, this is the action associated with a Dirichlet variational principle for the subregion, which means if I vary this action, I get bulk equations of motion. And then on the boundary, T, I'm going to get something that involves only a variation of the induced metric. And in principle, there can be an exact piece here which localizes to the past and future boundaries. And again, we're going to mostly drop those for this talk. They'll just show up in one place where I'll just mention them. Okay. And so these momenta take the form that should be somewhat familiar if you do GR at all. So Ij over 16 pi g. So it's just this thing constructed from the extrinsic curvature. And okay, yeah, so that's the Dirichlet action. And so the idea of Brown and York is that they're going to consider the classical action associated with the subregion, which just means they're going to impose the bulk equations of motion. And when you do that, then you see, so if this is 0, then the classical action is, its variation is purely written in terms of the variation of the metric. So the classical action is then taken, classical, is a functional of the metric on the boundary. And this is the thing that you now vary when constructing a stress tensor. And yeah, so as I mentioned before, the stress tensor really is supposed to measure the response of your action to a diffeomorphism. So we take some vector CA, which is going to be tangent to the boundary T. So it would be something like this, some diffeomorphism. And we want to see how the classical action varies when I, transform the fields according to that diffeo. Okay, so we have delta C of the classical action. This term is 0, and it's just, and we're going to drop again these terms that localize to the corner. And so this is just given by this integral of I Cj. And what we want to do is write this in the form of essentially a total derivative term minus essentially this separate term, which is a flux term. So once you have an equation like this, you can uniquely decompose this into a total derivative term that kind of accounts for the derivatives acting on C, and a separate term where both J and F depend algebraically on C. So there's no derivatives in J or F. And so J is how you're going to read off the stress tensor. This is essentially the definition of the stress tensor, is that J is C dotted into something like that. And this F term is then interpreted as the divergence of the stress tensor. Okay, the volume form.
So eta is like the normal, what's eta?
Eta is again the volume form just on the boundary. Yeah. Yeah, so I'll try to use that also in the null case, that epsilon is a bulk volume form and eta is a boundary volume form. Okay, and in this case, this divergence is just this the thing that you're used to here.
So I understand physics. So basically you integrate the work, right, by plugging into classical solution, right? And then you get a functional, which is functional boundary conditions.
Yeah, so this classical action, I impose the equation of motion. So then this guy purely depends on the boundary value of the metric here.
Then is H, should I view H as a dynamical object or just a source to prove the quantum numbers or charges?
Yeah, so essentially we're going to let it be arbitrary, but like if you're doing a variational principle for the subregion, you would kind of impose Dirichlet boundary conditions.
Okay.
So in particular, if this was a holographic setup, you would be fixing the boundary metric in the CFT, but you want it to be, you want to know what it is for every value of the boundary metric because you want to vary with respect to it to get the stress tensor.
Right, so in the holographic setup, then you're asking what are the global charges which comes from the Burke diffeomorphism, right? If you send to the.
Yeah, so yeah, we're constructing charges associated with bulk diffeos, but bulk diffeos that, you know, asymptote to a vector on the boundary. So really it is a boundary diffeo. So, you know, in holography, you take these guys to be your killing vectors on the boundary, and those would give you the charges. But more generally, you can even, so this thing about if it's a killing vector, then it'll be a conserved charge, but more generally, the stress tensor will just be measuring this response of the classical action to any diffeo, essentially from this equation. So, so from this equation, you can read off the Brown-York stress tensor.
Just so I'm following here. So eta I is what? And so eta is the volume form.
Yeah, sorry, I'm using this shorthand notation where I'm only showing which index I'm contracting. So eta has a bunch of suppressed indices. Does that make sense? I'm just showing you the first index of eta, but it's actually a volume form.
Okay, thank you.
That's just to write the contraction. Yeah, yeah, thanks for the question.
What's the F term?
The F term is, so it's essentially the divergence of the stress tensor.
Along the boundary direction.
Yeah. So yeah, I was going to say a few more words about this. Essentially, this F term is actually just zero by the bulk equations of motion, because okay, let me just write the formulas out. So using these as definitions, we get that Tij is equal to well, -1 over 8 pi g times Kij minus Khij. So it's just constructed from those momenta. And then this divergence of Tij, if you look at this for a second, you'll realize that's just the constraint equation associated with the timelike surface. So this is essentially zero by the gravitational equations of motion. And then this is this F term. So in general, this F term is just zero by the gravitational constraint equations on the surface.
No matter what was inside the boundary.
Yeah, so you need the metric to be, it's an equation of motion that this is 0.
Well, I guess what I'm trying to understand is it measuring some sort of energy flux out of the boundary, or
Well, no, it's 0. Is the
no
thing.
matter what kind
Yeah,
of
so I mean, this is
configuration I
just the
have?
statement on the boundary. Your stress tensor is conserved. And basically, your stress tensor is covariantly conserved, regardless of whether or not you have symmetries around. Their stress tensor is just kind of a covariantly conserved object. And so there's no source for the boundary stress tensor. If there were matter fields around, you would get contributions from the matter term. So the divergence of the gravitational piece is equal to the divergence of the matter piece, if that makes sense.
Okay.
Sorry, was there a question or?
I think maybe he didn't review himself.
Oh, okay, I'll just keep going.
Did you say you're imposing Dirichlet boundary? I
It's-
think you mentioned Dirichlet.
I'm writing down the action associated with the Dirichlet variational principle, but I essentially want to consider the action for every value of that. So it's not like I've fixed the metric on the boundary necessarily. I'm just saying this is the action that would be stationary if I did fix the metric. If you do impose Dirichlet boundary conditions, that's like a necessary condition for some of these charges that we'll construct to actually be conserved.
And this boundary is in the bulk, right? You're not taking, this is not an asymptotic boundary.
Yeah, so for simplicity, I'm doing this for finite boundaries. I'm going to comment in just a second on what you do for asymptotic boundaries. Asymptotic boundaries in this setup, you just want to think of as a limit of finite boundaries. And there's an extra step that's involved that essentially you need to add more than just the Gibbons-Hawking term to your action because you want things to be finite as well. Okay, so yeah, this thing, so it's good to keep in mind that this conservation equation of the stress tensor is the gravitational constraint equation, because that's going to show up in the next one as well, in the null case. Okay, and then the final point is something that I mentioned is the comparison to canonical charges. So you can construct charges associated with a localized space, which they're not like conserved charges, because if we don't impose the Dirichlet boundary condition, you should expect to lose flux to the subregion. But then there's this, what goes by the terminology Wald-Zoupas charges. Which is essentially set up to allow for such fluxes. And so they're charges that are conserved up to fluxes, basically. Okay, so you can go through this canonical setup, it's something that we did in the null case in quite a bit of detail in this paper with Ben from last year, but I'll just state what the result is that these charges are given by the integral of a charge density that I'll call H sub C. Okay, you can write it as the sum of 3 terms. Okay, so this thing is this another potential associated with diffeos in the bulk. Sometimes it's called the Komar charge. I'll just write it. Epsilon AB del AXCB. And again, this is this condensed notation where I'm suppressing all the indices that aren't contracted there. L here is that boundary term, so that's just the Gibbons-Hawking boundary term. And this is just denoting contraction of C into that differential form. And then this beta term is a contribution from this corner piece. Did I write it down? It's that thing that I told you I wasn't going to talk much about. So for the purpose of this talk, you use it to construct these charges, but we don't need its exact form.
Is that just flux going out of the corners of your spacetime?
Is what that?
This beta term?
Yeah, it's related to It's so those dot dot dots things.
Yeah.
So the beta is related to kind of corner terms that you would add at those codimension 2 defects. If you've heard the terminology Hayward term in the gravitational action, it's kind of related to that. So, so there's kind of an interesting story there that I just I'm not going to really talk about it here, and it's maybe not fully. I don't think I know fully all the details, but I think they're interesting. But apart from constructing these canonical charges, we don't need this.
So these are conserved, not conserved charges, or conserved.
So these are, unless you impose some Dirichlet boundary condition, and in particular, that means you need to take your vector field C. So these are constructed in terms of a vector field. It needs to generate a symmetry of your fixed boundary metric. So if the C generates a symmetry of the fixed boundary metric, and on top of that, you're imposing a Dirichlet boundary condition, they will be conserved. But more generally, what you can show is that this HC, its divergence is essentially equal to, there's maybe a factor of 2. Well, yeah, let's write it like this. Okay, so this makes it clear that if this is a symmetry, then this charge will be conserved. But you can see this is the same thing that showed up in the variation of your action. And so in particular, this is equal to d of jc minus fc, which is 0 on shell.
The boundary of finite distance. What does it mean to say you're fixing the metric on that boundary? I mean, it should have been dynamical, right, in the full theory.
Right. Yeah. So it's essentially if you want it to be conserved, you've essentially put a wall where you said I want to fix the metric there. But you can still define these charges. They're not necessarily conserved. This Wald-Zoupas procedure says essentially that they satisfy this, which you can do as like a continuity equation for them. It's that they're not conserved. They're given by a well-defined flux, which is this piece. Yeah. But the point is they're equal. So the d of this one is equal to the d of your Brown-York charge. And furthermore, these two guys are covariantly constructed from this vector C. So there's a theorem that is due to Wald that you can actually conclude that these two guys are equal from that. And it kind of boils down to just working out if these two things are identically equal, what could they possibly be? And it's just, okay, you can uniquely construct what they are. Okay, modulo an exact, maybe an exact thing, which will integrate to 0. So because these charges are going to be integrals of these currents over these codimension 2 cuts. Okay, so that's mostly the full timelike case. The one thing now I'll comment on is this idea about what happens at asymptotic boundaries. And the only issue is that this classical action as written will generically diverge if you're taking your boundary to be, asymptotically far away. And the way that's dealt with in holography is this holographic renormalization procedure where you add counter terms to that action. And so for asymptotic, we want to add additional boundary counter terms to make the classical action finite. And these counter terms are required to be functionals, purely covariant functionals of the induced metric Hij. And this requirement, as long as this is a diff invariant quantity constructed from that metric, that will preserve this property that the stress tensor is conserved. So these counter terms add additional pieces to the Pi just coming from varying it. And the diff invariance of those terms will show that each individual term is kind of identically conserved as this kind of a set of, essentially a set of Bianchi identity is associated with each counter term that you wrote down.
There's nothing ABS-ish about this statement you made. This could be a timelike boundary in any spacetime, or
Yeah, I mean, this is definitely used in ADS. So when they do holograph, this is what holographic normalization in ADS is.
right,
Yeah.
but the way you framed it, it doesn't
It's
require ABS anyway.
no, yeah, no, you can continue to write down the counter terms. This currently is kind of using that it's a timelike boundary. So there's definitely questions of how this works in flat space where you're asymptoting to a null surface.
Will you be able to answer that and using?
So essentially, yeah, I'm not going to answer it in this talk. It's probably just like a question of what exactly you do, because it's not clear if you should even, there's sort of different things you can do. You could take a limit, you could have a bunch of timelike surfaces that are kind of becoming null, or you could have a foliation of null surfaces. Yeah, so it would be interesting to check what happens in each case. And even when you have null surfaces, it's not as easy to write. So for timelike surfaces, you just know all the different variant things that you can write down. You get your Riemann curvature tensor and you form scalars from it in derivatives. So the null case that we're going to discuss, it's less clear what exactly all those different variant things are.
Sorry, in flat space, if I take like a cylinder and take its radius to infinity, I don't go null, right? I just end up at the corners of my.
Right, so that one you would end up like at kind of at spatial infinity.
Yeah.
And yeah, there's questions of how exactly you take these limits, because you can also, if you want to end up at null infinity, you can get there essentially from a limit of timelike surfaces as well, or depending on
Okay,
the conformal gauge that you're in and things like that.
So in the holographic case, right? Once we send say the boundary to the asymptotic boundary, and it is associated with actual like renormalization scale in the 40 sense, so it's clear that it is a UV divergent kind of thing that will solve those problems. But is it clear that this will be the same case even for other arbitrary timelike boundaries where you don't have necessarily the dual picture correlation between sending to infinity versus like length scale? How would I know that the sending this boundary to the infinity is always captured by the trouble is always captured by the local counter term versus there's other subtle more like, for example, instead of UV ultraviolet, how do I know there can be some infrared problem? In ADS,
Oh, you're
it's
saying,
clear,
well,
yeah, because sending it to the asymptotic boundary is associated to the UV direction. So I know it's going to be UV divergence.
You're thinking like an infinite distance into the bulk? Is that what you're saying?
Yeah, I'm just sending your cell into the infinity.
Yeah.
But in ADS case, sending that direction corresponds to the sending into deep UV, and I know that it's going to be ultraviolet divergence that causes me trouble.
Yeah.
But in other timelike boundaries, the story, which is not necessarily ADS CFT, how would I know that sending this to the boundary corresponds to always UV trouble like that?
Well, I think you can argue, there's probably a general argument that the divergences in that action are going to be coming from sending the surface out to infinity. Yeah, I don't, because otherwise you would need something like an infinite distance into the bulk, and okay, you'd have to have some setup where, I don't know, you need like basically an infinite distance. You need something to be getting infinitely big to get a divergence. That's
Yeah, maybe true. It's just on that.
You can see how it scales with radius, right? It's the action. You can tell exactly how it's scaling as you go to the boundary. Is that the issue you're asking? How do I know what counter terms to add?
I mean, there's going to be a sequence of counter terms that scale differently because they each come with a dimensional coefficient. Okay, yeah, dimensional. These counter terms eventually, it'll be curvatures and then curvature squared and so on. So those will all scale differently.
If I start with Einstein-Hilbert, I need a sequence of counter terms.
Yeah, depending on the dimension, this is.
But it eventually terminates. There's a finite set of terms.
Yeah. Yeah, essentially it says that that action will diverge at a certain power of the radius. And so you add one for the leading, and you have to cancel a subleading and so on.
I'm not sure, I mean, I wonder if that requires the boundary to be projective boundary, meaning like, but as in the case of ADS-CFT, right? As you said, there's all conformal structures, everything accumulate to the same structure, but just that the scale for the renormalization gets changed. What if your this thing is not that kind of structure? I don't know.
Yeah,
Maybe
I mean, I think that it's most clear here where you have a sequence of surfaces that are just getting infinitely far away. And I think you can kind of argue fairly generally that you should be able to cancel this with local counter terms. Yeah. Okay, hopefully I can get to the stuff. So in order to talk about the generalization to null surfaces, I have to do a detour on describing what the geometry is on null surfaces. I'll try to go a bit quicker. So the question we have to answer is kind of what is the analog of this Dirichlet action for a null boundary? Okay, so I'm going to draw the picture again that you should have in mind. So here we've got sort of a subregion U, and now this boundary is now going to be a null surface like this. Okay, and I've reduced the dimension for drawing purposes. And so the question is now, what should you say is the Dirichlet variational principle when you have a null boundary? And so this was something that we looked at in this paper here. And we were arguing that the way you should set this up is that not only should you fix sort of the null surface and the metric on it, but you should really fix the null normal NA to the null surface. So by fixing a null surface, you're sort of fixing the normal up to scale. And the thing we wanted to argue is that you should actually fix the full null normal. And so what this determines at the null surface is you have the induced metric, which is degenerate on the null surface, but then you also have a preferred null generator on the surface and upstairs. So since it's a null surface, the normal, when you raise the index, becomes a tangent vector. And then the fact that Q is degenerate and N is a null generator just means that NIQ IJ equals 0. So this data now sort of parameterizes the Dirichlet data that we want to use, and it's analogous to HIJ. And if you want to count components, say we're in 4 bulk dimensions, so the induced metric on the boundary is going to have 6 components as a symmetric 3-index or 2-index tensor. And then this guy is a degenerate metric on, so it essentially has 3 independent components because it's essentially a 2D metric. And then this has 3 components. So this is 3 plus 3 is 6. So it's the same amount of data that is being fixed. And so in general, if you have any surface that has a degenerate metric and a preferred null generator satisfying this equation, this is all we mean when we're talking about a Carroll geometry. So this is what a Carroll geometry is. Just like a non-degenerate metric will give you a pseudo-Riemannian geometry. Okay, and so in order to set up the whole variational problem, I have to review a few of the structures that you get for free once you have this Carroll geometry. So there's sort of 2 volume forms that are now naturally associated with this. You have sort of a spatial volume form, so called mu. You can think of, it's the thing that if you took a slice of the null boundary, it would be the volume form on the now space-like slice of that surface associated with this metric on that slice. But then there's also a volume form on the full surface. So this is just a regular volume form. And it's the thing where if you contract with the null vector n, which is fixed, it gives you back this spatial volume form. And then you can define some first order differential invariance. So if you take d of mu, this is proportional to eta. And the proportionality constant is just the expansion of this sort of null surface. And you can write things like the extrinsic curvature by taking the Lie derivative of this metric with respect to the null generator. And this is the extrinsic curvature in quotation marks because it's completely determined by the intrinsic quantities, but it's sort of like the combination of the shear and expansion of this null congruence. Okay, so in addition, if this surface is embedded in space-time, there's going to be some intrinsic or extrinsic quantities that you want to define as well. Yeah.
Is fixing n the same thing as fixing an affine parameter?
Yeah, because I guess you can pick the parameter such that n dotted into that parameter is 1. So yeah, picking an affine parameter will fix the normalization of n. Yeah. Okay, so now in space-time, this null normal NA has a covariant derivative. And you can essentially pull back this index. So okay, I'll use this notation pi that just means pull back the index to the surface. And this is tangent on this B index. So this defines a tensor that's well defined on the surface, which I'm going to call Wij. Okay, you can define it by this equation. And this thing is called the shape operator of the surface, or the Weingarten map. And it's exactly analogous on a regular surface to the extrinsic curvature. So this would be Kij. I'll say it's like Kij for timelike. On the null surface, it's important that this has to come as a mixed index object. And it's, for example, it's spatial components. So if you lower the index with the degenerate metric, it gives you back this this extrinsic curvature we mentioned over there. So more generally, you can write this guy. You can decompose it. So the components that aren't fixed by Kij are given by this object rho, which we call the rotation one form. Okay, and I'm gonna write Kij now as a mixed index thing. So in order to raise in spatial indices, you have to introduce an auxiliary null vector to define what that means. But okay, I think I'm a little short on time, so I'll just, if you have questions about how this definition works, we can talk about it afterwards. But the final point is this rotation one form now. Decomposes like this. J. Okay. So it involves a term that's sort of, this is this auxiliary thing that I just mentioned. So this is sort of the time component of this rotation one form, and then a spatial component, which is known as the Hadjichak one form. And this K right here is the infinity of the surface. So this K is defined by the equation NA del A NB equals K NB. So in space-time, your null generator is a geodesic, but this K is measuring the extent to which it's not affinely parameterized. Okay.
You pick an n to K0.
Always. So the way it's set up is that we're saying n downstairs is fixed. And so then once you fix that, depending on what the metric is, and this will be affinely parameterized or not. So the point is that this k is now a metric degree of freedom once n downstairs is fixed. So it's an additional boundary condition if you wanted to fix it.
What is the meaning of fixing n downstairs? So I'm not allowed to rescale.
Yeah, so I'm saying don't rescale. It's literally you're setting, if you set up your phase space, it's literally I'm just putting a background field and downstairs. And it's just you're restricting the metric that to make sure that it stays null. So you're going to say that NA dot NA is 0 at the null surface, but otherwise it's just a background field.
So under rescaling, that won't change that property, right?
Yeah, so you're essentially not allowed to rescale at downstairs in this setup, which is, so this is the point. So there's more information than just having a null surface now. And that's what leads to this Carroll structure as opposed to just a null surface with a degenerate metric. So the rescaling is the extra degree of freedom that's around. Okay. I have some stuff on connections related to the Carroll geometry, but I'll just mention it when we get to the conservation equation for the stress tensor, because I want to try to show you what you now use all of this setup for. So essentially, we needed to do this just to write down the whole variational principle for the null boundary. And so now we're going to do the null Brown-York charges. Okay, so now what we need to do is be able to write down the subregion action. So again, it's going to be integral of the Einstein-Hilbert term plus a boundary term integrated over the null surface. And this boundary term that's now associated with the Dirichlet principle, which means fixing Q and N upstairs, is constructed from this infinity here. And it kind of looks like, the Gibbons-Hawking term. It's essentially where you take lowercase k to be the Gibbons-Hawking type term.
So I thought myself confused. It's very basic. What's the relation between n lower a? N lower a is normal to the null surface?
Yeah, so I'm writing n lower a is the normal vector. So the null surface, the tangent directions to the null surface are things that annihilate n downstairs. So any vector that dotted into n downstairs is 0 is tangent to that surface.
Okay.
And then when you raise the index, because it's a null vector, you know, n upstairs dotted into n downstairs is 0, so n upstairs is tangent as well.
Good. Okay. Okay. So n upstairs, you're labeling as n I.
Yeah, and so the ij just now means take it as an intrinsic on the surface.
Okay.
Yeah.
Good.
Yeah, sorry, yeah. So ABC are space-time indices for me, and IJK are one dimension down. Okay, so when you write down this boundary term, your Dirichlet variational principle now takes the form delta S is equal again to the bulk equations of motion. Plus the integral over the boundary of pi ij dotted into the variation of the degenerate metric plus a momenta associated with the variation of the upstairs n. Okay, plus the corner term again, which is being ignored for this talk. And these momenta are now given by, get the coefficients correct. Okay, so this looks kind of similar to the timelike case, but it now involves this expansion and an infinity. And then the vector momentum expression. have a volume form out in front. Okay, but it involves the expansion, this auxiliary vector, and this Hadricek form. Okay. So these are going to be the objects from which the stress tensor is constructed. So now, as before, we want to consider the classical action, which now we see the classical action is now going to be a functional of this intrinsic Carroll structure. So S classical is a functional of the Carroll structure. And we want to consider its variation with respect to a diffeo that acts on the boundary. From taking this equation, this is just going to be pi ij. We see qij plus pi c n I. Okay. And as before, we want to write this as dj c minus fc. And we're going to use these two equations again, this relation to determine our stress tensor and the divergence. So this one will give you the stress tensor, and this one gives the divergence of the stress tensor. Okay, so we get jc is equal to tij cj theta I. And from this equation, we get tij is equal to 2. Okay, you gotta just put the eta on this side. 2 pi I k q k j minus pi j and I. Okay, so this is kind of the generalization of, this is what you get that generalizes the equation that the stress tensor should be the variation of the action with respect to the metric. It now involves a variation with respect, so this guy comes from varying with respect to the degenerate metric, and this one from varying with respect to the vector. And if you plug in the expressions we have here, we get tij. This really simple form in terms of this shape operator that I wrote, delta ij, where w is just the trace of that. And so this is essentially the exact same expression as in the timelike case, where I replace the extrinsic curvature from the timelike Brown-York stress tensor with just wij, which is the shape operator. And so, yeah, I think this is like a nice, compact, simple expression for tij. It's kind of, it has a lot of nice properties, like it doesn't depend on this auxiliary structure that we introduced. Okay. And then finally, this equation also defines a covariant divergence. So we just define fc to be the divergence of the stress tensor. Okay, do I want to write this out? So essentially, this divergence and kind of looks like this. Minus rho I tij minus I k d j k. A minus pi I dj and I. Okay, so it's this generalized expression that involves so here this d is any connection that you put, it's any derivative operator that you put on the null surface. You can show this expression's independent of a choice of derivative operator. And it involves contributions that come from like the failure of this connection to be metric compatible, because in general, you don't have a metric compatible connection on your surface, and similarly for the ni. But the last thing we showed is that for a certain class of connections that are naturally induced from the extrinsic geometry, you can show that all of these terms cancel. So in the end, you do get just this conservation equation. Okay, so we'll put a star for a special class of connection. It just looks like the ordinary stress tensor conservation equation. And the final point is that this thing, again, is equal to 0 by the gravitational constraints on the null surface. And so these constraint equations, if you decompose this into the time component and then the spatial component, the time component would be the Raychaudhuri equation for the null surface, and the spatial component is what's been called the de Moivre-Navier-Stokes equation. So de Moivre had this work where he was viewing these constraints equations on black hole horizons and interpreting them as a fluid equation. And one of the upshots is this sort of explains why you're getting a fluid description for null surfaces in general. Essentially, the constraint equations can be rephrased as a conservation equation of a stress tensor, and hydrodynamical equations are just conservation equations for stress tensors. So it puts a nice it has a nice connection to, fluid gravity and, hydrodynamics in gravity, where you just interpret that constraint equation as a conservation equation.
So what is the precise condition to achieve ultimate 0? You said that there should be some cancellation if you choose some nice structures, but if not, they may not be 0 eventually.
Yeah, in general, you want to use this equation for the definition of a divergence. It's just there's a class of derivative operators where, and the specific form of pi ij and pi ik, which I wrote up there, where all of these terms cancel out. So it's a bit satisfying. It wasn't really necessary for that to happen.
Okay, so then overall equation for charge, like run your charge is the dj c minus f. That thing is equal to dh something eventually, I guess. No?
Yeah. So again, the fc again was this divergence.
Yeah.
And so that's 0 on shell.
Only if you choose good.
No, it's this thing. It's this thing is 0 on shell.
Oh, that's
These are the same equation. It's the star just means I picked a special
I'm sorry.
connection. Yeah, maybe I'll call this a D star. I don't know. It's just, yeah, there. So that's 0 on shell. And then again, as Sungwoo was mentioning, you can, this equation you can show implies that the canonical charges that you would write down using this Wald-Zoupas procedure is equal to djxc. And you can conclude the two charges are equal. I should mention the Wald-Zoupas charges that you construct. There's some ambiguities in how you construct them, and essentially you resolve those ambiguities essentially by appealing to this Dirichlet variational principle, and those are the charges that match these, which you should expect because the whole construction was a Dirichlet construction. Okay, so I think that's a good stopping point. I could maybe maybe I'll just review. So the point was we wanted to show how to construct this Brown-York stress tensor on a null boundary. So the Brown-York construction was originally just for time-like boundaries. And so there was a number of subtleties you have to address related to the fact that your geometry is that of a Carroll structure as opposed to a Riemannian structure. But we end up with this nice simple expression for the stress tensor, and we showed that it again is conserved as a consequence of the gravitational constraints. So that's analogous to the timelike case. And more generally, if you were interested in holography, so this would be like if you're trying to set up a holographic theory associated with such a, with such a Carroll structure. So you're trying to put a field theory on a null surface that's responding to this. And essentially this equation is always the type of equation you're going to write down for the stress tensor in such a theory. So presumably this ought to eventually become relevant if you're thinking about flat space holography where you are dealing with null surfaces, or I don't know, people think about BMS field theories and things like that. And so it's an interesting question. The celestial holography program has they have a somewhat different construction, but there is a stress tensor in their game. And it'd be interesting to try to relate this to their stress tensor. And another thing that's also an interesting question that I don't think is fully resolved is this idea of counter terms and how exactly you do the counter terms when you're going out to null infinity and asymptotically flat space. And there's kind of questions of whether you should consider a sequence of timelike surfaces or null surfaces. And this question of whether your counter terms continue to satisfy this conservation equation will depend on the covariance of the counter terms that you find. So this is a motivation for finding not just like any random counter term, for finding like appropriately covariant counter terms to do holographic renormalization in flat space. And finally, as I mentioned, there was a couple places where I talked about corners, and there's kind of a whole interesting story there where you're more careful about these types of corner contributions. And so there's some kind of interesting charges associated with those as well. Okay, so anyways, I'll stop there and take any more questions. So thanks.
Still true that I think of charges in field theory as the thing that generates. I guess in this case, translations and so on. Like regardlessly, it seemed like there was some debate over what the right counter terms are and so on. Does any of that have any bearing on the action of these charges? If I think of them in a field theory as acting on the fields in my field theory.
The counter terms?
Yeah. Do they show up at all?
Do they still generate? Yeah, I think that, I mean, the counter terms, it's more like just.
It's just a total.
It's like in holography, they're like, it's related to the renormalization of your operators. Yeah. There's an interesting question about anomalies and how those show up, which I didn't really get into here. But in holography, you have these holographic Weyl anomalies, and it essentially comes about from the failure of various things that you wrote down to be completely covariant. So like your boundary terms will end up not really transforming covariantly under a diffeo in the bulk. And in ADS, it's also related to the fact that you have when you're going out to the boundary as a sequence of cylinders, your transformations do have a small radial component, which kind of are a compensating Weyl transformation. And those can induce anomalous transformations of various objects. But yeah, okay, I don't know.
You're saying as far as the actions on the fields that are concerned, you're basically blind to these counter terms. Yeah,
because usually, specifically for asymptotically ADS, you are imposing like a Dirichlet boundary condition at the end of the day.
Well, for ADS, I thought everything
then these counter terms are kind of constants, basically. And
you're saying the same thing is true if I'm worrying about scry.
Yeah, so yeah. I don't know, scry is kind of interesting because you generally do allow fluxes out of scry. You want like gravitational waves to come out. So there you impose less strong boundary conditions. I think that was kind of the motivation for considering this Wald-Zoupas setup. So scry in some sense is a little more analogous to finite boundaries in the sense that you don't really want to impose the boundary conditions. So the extent to which these charges generate the symmetry on the phase space, yeah, so they sort of do, but I think that they don't quite. When you have fluxes, they're not actually. If you wrote down a phase space and tried to compute, Poisson brackets, there's going to be somewhere where you can detect they're not actually generating the phase space because it's not generating the symmetry. So it's because it doesn't satisfy Hamilton's equation. So, but they sort of do as good as you might have expected, given that you're losing flux.
Is that something that I can fix by adding counter terms, or you're just saying if there's a flux, I can't?
Yeah, it's more that if there's a flux, you probably shouldn't expect to have you don't expect the like a BMS transformation to be generating a symmetry on a phase space associated with, you know, everything to the future of a cut, because you're just losing flux. So I'm just saying that you wouldn't expect it to be generating a symmetry, but these charges are somehow still relevant in that case. So in particular, you can construct these charges and an algebra for them, and they, in a certain sense, reproduce the BMS algebra via Poisson brackets.
So I'm still confused as to how I'm supposed to think about these charges in the situation where the surface you're talking about is at some finite position. So what is it that they're measuring? I mean, they're not globally conserved, right? They
Right, you should expect them generically not to be conserved. The only time they would be conserved is if you have a subregion that has a killing vector on the boundary and you're constructing the charge for that. So, you know, outside of a black hole, if you take a surface that follows the killing flow, there's going to be a conserved charge associated with that. But otherwise, generically, they're not conserved. And yeah, it's just
they're sort of like they're not dynamically conserved, because dynamically, for instance, the killing vector will be destroyed by throwing in some stress energy.
right. Yeah. Yeah, and so all that means is that if you measure them at one cut versus another, there's a difference, and that's given by this flux term.
So if I had some perturbation, it fell through the horizon, before and after I would have this charge, and then is there some statement that the change in the charge is related to the flux of what I threw into the horizon?
Yeah.
Yeah.
Yeah. Let me see, where's the equation at? It's essentially, I'll just rewrite the equation, but it's something like djc is equal to, just for say the timelike case. So if you integrate this between two cuts, you get the difference in the charges on this side is equal to the integral of this thing, which you interpret as the flux through the horizon.
Okay, thank you.
Yeah.
If I just take Minkowski spacetime and I go to Scry, view that as my null boundary, and look at your Tij, can you say anything about what kind of field theory or theory could be existing out there on which you would have some action of BMS or something?
Oh,
You
you're asking what kind of theory would have this?
yeah, what kind of theory would have a stress tensor like this?
Yeah, it's not something that I think there's been a couple papers where people have tried to think about this question, but yeah, it's a theory that would be defined on a null surface. So there's already kind of questions of what that means, because there's, you know, if something's on a null surface, you expect it to be kind of ultra local, like you don't really expect correlation between different points that aren't on the same null generator. So yeah, I don't know all the details behind, I mean, people have tried a little bit to understand this. There's these BMS field theories. Yeah, I would have to look up the references, but people have tried to think about it. In that case, it's like if you do it in 3D, I think you're essentially trying to construct a field theory that instead of, for example, well, yeah, they want an action of this BMS3 group, which is like half Virasoro and then half super translations. And so it's supposed to look like a weird modification of like a 2D CFT. But yeah, I don't know in general what these theories would look like. It's just that it's possible that they would come up when you restrict theories to null surfaces.
So could you have asked that same question in ADS and you would have just said conformal symmetry? You're asking what are the representations maybe of this group or something?
Yeah.
What the
What
You know, what the labels.
It's just in that case, you know what theory you're looking for a conformal field theory there.
What kind of theory? On what kind of theory could you implement, say BMS3 or BMS4, whatever dimension you want to look at? And is there some kind of sensible theory at Scry that you could do this for? Maybe two theories, maybe Scry minus Scry plus some fluid or something. I don't know.
Yeah, so yeah, I don't know if there really is an example of it. Somehow in some sense, I feel like what the celestial CFT program is doing is it's kind of trying to construct a theory like that, but it's also like taking advantage in some sense of this ultra locality of the null surface, and it reduces it down to an actual, some sort of 2D theory.
Yeah, getting rid of the, but in 3 dimensions, that would get you just a theory on a circle or something.
Yeah, that's true. Yeah, okay, yeah. Yeah, I'm not,
Quantum mechanics, or some kind of quantum mechanics. Whatever that might be.
yeah. Yeah, I'd have to look up, there's some work by, okay, there's like Bagchi or something and some collaborators that were trying to write down like BMS3 field theories, and I'm not exactly sure what.
It's a circle times a man, null direction, right?
Yeah, but say in the 4D picture.
They kind of reduce it, yeah, they try to reduce the null direction.
direction to collapse the sphere, right?
Oh, is there a free field theory version of this now? Like, you know, I know that free scalars is the simplest theory with Verilsero. Is there a BMS version for free field theory?
Free scalars.
Yeah, I mean, you might try to put like a free scalar on just a null surface. I think actually that's what, if you feel like this thing where you try to restrict a quantum field theory to a null surface, that might be an example of that.
I think it'd be very degenerate. You try and do that. I mean, it'd be very hard to make sense of. I just want
Yeah, it's degenerate, but it's something that, I don't know, people used in these like generalized second law type proofs. They
Let me
were
ask something even more basic. What, like in Verilsero, I know what to label my representations. They're labeled by weights and so on. Is there, when I look at the BMS algebra, have people worked out what the representations are, ladder operators, blah, 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 and what things are labeled by?
Oh, for BMS4?
Sure.
Yeah, it's a question, well, yeah. I think maybe just for pure BMS4, I think people looked at it a little bit, but they're not so interesting. I think then the celestial holography now starts including these super rotation type transformations. So then it starts looking more like CFT type constructions, because there you actually have a Virasoro algebra around.
So when you say it's not interesting, I mean, it's still what I'm going to label my state. Whatever my field theory is, that's how I'll label the states in whatever the definition of state is for something that doesn't have a Hilbert space.
Yeah, what do I mean by it's not interesting? Well, I don't know. Some people were looking at this a long time ago, and I think it was just kind of weird in the sense, like there's some results by what's the guy saying? I think it's like McCarthy from the 70s, where he was just trying to look at he was just trying to say, how do you do this classification of reps of BMS, kind of just like you would for reps of Poincare. So if you do reps of Poincare, that's how you get field theory from Weinberg's type.
Yeah.
So he looked at that, and there were some random results, like I guess he found some of like the continuous spin representations weren't there, but then there's also, yeah, some of the labels. It was something like most of the time you don't get like spin for your particles or something. It was something weird. I'd have to look at it again, but yeah. Yeah, I think these days, like what the celestial holography people are doing are seeing if they can get more information by including like super rotations as a additional label. And I guess they're proposing other symmetries as well. But
This basic representation theory exercise is not something that they think is important.
Well, no, I think some of the stuff they've done is looking at these representations. because they've been talking about they have an SL2C, and so they talk about the reps of SL2C, and so there's some information about that. So your global conformal group.
Yeah, the global conformal group is supposed to be BMS, right?
That's right. that's-
Yeah, so the global
think that-
BMS is that plus all this, but then you have all the super translations, so those are the ones that make things a little funny.
Is light cone quantization not an example of this?
Yeah, I think, okay, I was trying to refer to, I was thinking that might be an example, yeah, where you put a field theory on a null surface. Yeah, that's what you're referring to, just like sticking a field theory on a null surface or something else.
How would that work? You want to light cone quantize a theory defined on a null surface.
You can define it in the bulk and then restrict it to a null surface.
Oh yeah, sorry, that's what I was, it's maybe like cone quantization is referring to something else though.
Yeah, light cone quantization will be bulk quantization, just in a particular gauge.
Oh yeah,
But
okay.
then would that make it, maybe that makes it easier to restrict to some kind of null surface. That would be matrix.
Okay, yeah, I'm not sure there.
Exactly. So here are you're not doing Virasoro or anything.
No, like essentially I'm doing, when I construct this stress tensor, I'm actually considering any possible diffeo of the null surface just to show you, that's sort of how I'm defining a stress tensor, is just response to an arbitrary diffeo.
But
In this paper with Ben from earlier, we did look at a set of transformations that do form a Virasoro algebra. And something I didn't talk about are this kind of concept of anomalous transformations. And so in that case, they explain these central extensions that appear there. But yeah, here I'm not really using Virasoro.
Do those transformations preserve your null, you have like this pair of symbols Q and N?
Yeah.
The
So
Virasoro.
so the Virasoro, the way you get the central extension is there are transformations that aren't preserving n downstairs. And you can consistently define their action on your metric, because fixing n downstairs doesn't really, apart from the fact that you need to make sure that it's still null, which the Virasoro transformations do preserve, but it doesn't, the fixing n downstairs doesn't put any additional restrictions on the metric, so you can still define a consistent action by vector fields that don't preserve n downstairs. But they lead to various modifications of the formalism. But one of the things we showed is that anytime you get a central extension in this charge algebra, it's coming from this type of anomalous transformation there.
Well, I think we should let the speaker go, and so it's thank the speaker when we're done.
People try to make